Now let's look at the total collision rate. So the total collision rate, and let's look at one we'll call Z11, which means we've got a bunch of molecules that are all the same. We could call them molecule 1. And we're not just looking at this one molecule and seeing how many collisions it has, but we're following all the molecules in this sample and seeing how many total collisions there are in the sample. And in this case, the sample is made up of a single gas. Well, in this case, it's actually fairly simple. We take the single particle collision rate and we multiply that times the number of molecules in our sample. Now, if we stopped there, we'd actually be overestimating by a factor of 2, because when this molecule collides, it collides with this one. And later on, when we follow this molecule, we're going to count that collision again. So we'd be double counting collisions if we left it at this. So we have to divide by 2 because each collision is shared by 2 molecules. And that's going to be equal to the overall collision rate. And if we put the equation for the single particle collision rate in with an equation for number density, we'll have a new equation here. So it's just Z1. So if we're going to multiply that by the number density of the gas, we would have P1 over KT again. And that's just the number density of gas number 1. And then we have to divide the whole thing by 2. So I'll put that over here as a 1/2 to avoid double counting. You can remember that mu for two particles that are identical, it's just the mass divided by 2. And we can move this KT into the square root to combine it. And we can combine all the numerical factors. So let's go ahead and do that. Let's say that this is the collision cross section. We have 8 pi KT cubed, because we have the original KT and then we're moving this inside the square root. We have the mass divided by 2 is equal to the reduced mass. We've got the pressure, the partial pressure of gas 1 squared, and then we can move this 2 into the square root. And we move that in, it's going to be a 4. So we can cancel this 4 with the 8 to give 2. And then we can pull that out since it's the square root of 4. So we end up with 2 times the collision cross section times the square root of 1 over pi times the mass. And then we can say we've got the pressure squared and KT to the 3/2. And that's going to be our final expression for the overall collision rate. And so this is going to give us all the collisions that occur per cubic meter. So this is going to give us units 1 over cubic meter, and of course per second. Okay? So that tells us how many collisions occur. If we had a box 1 meter cubed, how many collisions would occur in that box per second. We could do a quick example. We could ask, what is Z11 for, let's do nitrogen, 1 bar, 298 K. So we've got Z is equal to 2 sigma square root of 1 over pi mass P squared over KT to the 3/2. And if we wanted to, if you don't like using the small units, we can multiply the top and the bottom by a factor of Avogadro's number to the 3/2, and that'll turn your K's into R's, and then we'll have units of Avogadro's number up here. So we can plug this in, we've got 2 times the collision cross-section, which we can look this up for nitrogen-nitrogen collisions in your book, and we'll see that it's 4.3 times 10 to the negative 19th meters squared. We can do the mass of a nitrogen molecule, and we want the mass of a nitrogen molecule. Probably the easiest thing to do is we've got 28 AMU for a nitrogen molecule, and then multiply the mass of an AMU, 1.67, 10 to the negative 27 kilograms. So there's a mass of our nitrogen molecule, and then we multiply by the partial pressure. Remember, we got to put this into pascals. We can't leave it in bar, so 10 to the 5th pascals. We got to square that, and then divide by Boltzmann's constant, 1.38, 10 negative 23 joules per Kelvin. We're working at 298, and that whole term has to be to the 3/2. And we plug all that in, we end up with Z11 is equal to 4.3 times 10 to the 34th collisions per meter cubed per second. So we can see that they're not just billions or quadrillions of collisions per second in a 1 meter cube size of air. There's a huge number of collisions, so there's constant collisions of gas molecules at normal temperatures and pressures.